Welcome to Positive Physics, and today we're looking at visible light section of the electromagnetic spectrum. So the wavelengths we're talking about now are between 400 to 700 nanometers, 4 times 10 to the minus 9 to 7 times 10 to the minus 9 meters. So we've gone from radio waves to microwaves to infrared radiation, and now we're at the visible light section. And our shortest wavelength will be our violet wavelength, and our longest wavelength will be our red wavelength. So, primary colours of light, and remember there's a warning here, this is not pigment or paint. So this is not the primary colours that you learnt in primary school. This is the primary colours for light, and they're slightly different. We have red, green and blue, and when we shine those lights together, so for example when we have red and green light shining in the same place, if you were on stage for example, you would see yellow light produced. If you had red and blue light shining in the same place, it would produce a magenta white light, which is like a pinky purpley colour. And if you had blue and green, you would have something called cyan, which is like a turquoise colour, but it's called cyan. And these colours, the cyan, the magenta and the yellow, are the secondary colours of light, which are formed when you mix two colours of light together. That means you shine them in the same place. And the key thing is, when you take red light and green light and blue light and shine them all together, you end up with white light. The same would be true if you took red light and shone it in the same place as cyan light. These opposite colours here would produce white light together. Likewise, blue and yellow would produce white light, and green and magenta would produce white light. So we have our primary and secondary colours of light, not paint. So how do we see colours? Well, if we have white light shining on our juicy red apple and green leaf here, you have all the colours within the spectrum inside the white light. And everything, all the colours are absorbed except for the green. And the green is reflected by the pigments in the leaf. For the red apple, all of the colours in the white light are being absorbed except for the red, which is being reflected. And so it is the green light and the red light which reaches our eyes, and we see the leaf as green and the apple as red. Finally, our banana, we have two situations here. We have white light being shone onto our banana and yellow light being reflected. But alternatively, if we shone red and green light onto our banana, red and green light would be reflected. As we see here, the yellow is where red and green are both shone together. So if you shone red and green light onto our banana, you would get red and green wavelengths of light coming back to your eye, and to your brain would say it's yellow. Now that is really cool, and it's to do with the rods and cones in your brain and how your brain functions and analyses wavelengths. So I suggest you have a look at that, Google that, see how we see colour. Now filters are fairly straightforward. If you have a transparent filter or a transparent piece of glass, the white light that's incident on the glass is just transmitted straight the way through. If you have a blue filter, the white light is incident on the blue filter. The red, orange, yellow, green, indigo and violet have all been absorbed, and the blue light has been transmitted. If you then took that blue light and shone it through a red filter, the red filter would absorb the blue light and nothing would be transmitted. So this is key, because if you were to put a pair of red glasses on and look at something which was reflecting blue light, a blue box or a blue exercise book for example, it would look black because nothing was being transmitted through the filter. And where we have an absence of colour, something is black. Now, when we look at objects under different lights, they will look different. So here we have some rainbow clothes here, just to show the different colours. So we've got red, we've got yellow, green, we've got the cyan, we've got blue, and we've got magenta. Under a white stage light, will look red, yellow, green, cyan, blue, and magenta. However, under a red stage light, it looks very different. The red is still reflecting the red light. The yellow will also reflect the red light, but the green and the cyan and the blue all look black because there's no part of the red light being reflected, it's all being absorbed. Magenta, however, will look red because it can reflect the red light. If we viewed the same items of clothing through a green filter, so all the colours were coming from the clothing through the filter to our eyes, as if we've put a pair of green glasses on, you can see that the red, where there's no green in that light that's being reflected, is looking black. The yellow can look green, the green looks green, the cyan looks green, but the blue and the magenta look black. And if we go back to our original diagram, we can see that that is because these primary colours will make up the secondary colour. So if you've got a green filter, the yellow, which is green and red, would still look green. However, the red, the magenta and the blue, there's no part of the green to be reflected, everything's been absorbed, and they will look black. Now the final thing to say is that we know that light is made up of all the colours, and that's from an experiment that I expect you've seen with a prism, a triangular prism, where the incident light, there's an incident ray of light, comes in and is refracted. I'm just going to draw this second one here, nice square block. You all know refraction at the block, let's draw our normal in, because the wavelength, the light is slowing down as it enters a more dense medium, it bends towards the normal, and then where the two surfaces are parallel to each other, it refracts. There's another normal as it leaves, it refracts away from the normal and ends up travelling parallel to the incident ray. So that's refraction. And that's when the two surfaces are parallel. But when we use a prism, what we find is something slightly different happens. Now you'll have to excuse my purple, it's a bit thin, and my red. The red light has the longest wavelength, so it is refracted the least. The violet has a shorter wavelength, so it is refracted the most. Now, because we've got to another angled surface, the refraction happens again, and where the light is refracted away from the normal, we end up with our red being refracted and our violet being refracted, and all the colours in between, the orange, yellow, green, blue, indigo, are also refracted. And what happens is when you put this onto a screen, the colours have been split out, and this is called dispersion. So we end up with the electromagnetic spectrum, the visible spectrum from red to violet. And what's happened here is it's all spread out. Now you would have found at this point that the red and the violet had refracted differently, but because we're then coming to a parallel surface, when they were refracted here, they were refracted back to be going in the same path. So you end up with white light coming out. So you've got white light going in, refracted, white light coming out. Here we have white light going in, refracted differently in the prism, and then refracted differently again at this angle here, so that we end up with dispersion of our spectrum. And that is why we end up with our beautiful rainbow on the screen here. So it is called dispersion, but it's actually just refraction of the different wavelengths. So the red is refracted the least, and the violet is refracted the most. And that's due to their different wavelengths.